Today's topic is something called isolines, which we mentioned briefly in talking about how to represent potential graphs and functions. Consider a contour map. This, for instance, is a picture of a region somewhat to the west of Jenks, Oklahoma, and it shows us the lay of the land. Every line is a line of constant elevation, so the 750 line means that everything on this line is 750 feet above sea level. So, by the way, it turns out is this. If you look around here, they go here. And then everything on this line is 800. And the things in between are obviously in between that. And then this would apparently be 900. No, 850, sorry. This would be 850 line. They're 50 each. And then the 900 line and so on. So this point, anything on this line is higher than anything on this line by about 50 meters. Consider this blue dot and take a minute and think, if this blue dot were a ball that was able to move, to roll freely, and you placed it here and held it, and then you let it go so it could suddenly roll freely, where would it go? Sketch something, or in your mind's eye at least, sketch where you think it would end up moving. You probably would have said something like this. It would move, not surprisingly, downhill. And it would move downhill pretty much as directly as it can. You would be surprised to see it kind of meander this way, because this is less steep than this is. Right? It's more steep. For the same change in altitude of, say, here 10 meters, it does it much more quickly here than here. So you would expect the ball to roll down that way. All right, now put a star where the land is flattest. It says drag a star because this was a parodic operation where if we were doing this live, you could drag the star over to where it needs to go. But the thing here is look around and say, where does the land seem flattest based on these contours? It's not that easy to see, but probably this region, because the height doesn't change very much. It's, what did we say this was? This is 850. So it's between 850 and 840, but it takes a real long time. So the ground here is very, very shallow. The slope is very, very low because there's a really great distance, as opposed to going from here to here where it's pretty steep, or from here to here where it's relatively steep. The land is flattest where the contour lines are furthest apart, and it's steepest where they're close and dense. Using that thought, mark a region where the land is steepest. Try in your mind's eye to figure out where does the land look like it would be the sharpest drop. Where the contour lines are close together, the land is steepest. It's not that easy on this without doing actual measurements to figure out where it is actually, steepest. But this region, for instance, would be an area where it's pretty steep. We go from 950 to 900 in a relatively short distance. Maybe it'd be even steeper here. Maybe even in these regions. But somewhere where the lines are dense and less steep in this region. So if you were trying to draw how this might look from the side, you might say that there's something like a hill, and then it kind of dribbles out. And that's looking that way. Is looking that way. Something like that. I didn't do it with any kind of care, but that's what happens. Here's the payoff from our viewpoint. A topographical map like this is really just a contour of gravitational equipotential surfaces. Right? Remember from our strange parable of the two odd surveyors, the gravitational potential of something is essentially GH. And so contours would be the heights. So they're basically multiplied by G, and you have a map of the gravitational potential. Each line of constant height is what's called an isoline. Iso, of course, the Greek for same, like isotope or isotherm. We can analogize this to electric fields and say the following. Electric fields point down potential gradients. They point from regions of high potential to regions of low potential. They're always perpendicular to equipotential surfaces, and they're greatest when the isolines cluster and are least in regions with sparse isolines. By the way, let's talk a little bit about point 2 here. The electric fields are always perpendicular to equipotential surfaces or to or isolines. Why is that? Because if we have, here is our isoline, and here's like another isoline, and so on. If I move from here to here, the potential is the same at every dot in between. So there's no work done. And the other way there's no work done is if the force is everywhere perpendicular. But the force is the same direction as the field. And so there must not be any field along the potential. If there were field along the potential, then a point particle here would get work for free, even though it has the same energy. And that's obviously not possible. So anytime you have an isoline and you want to know where the field is, it's always perpendicular. But the strength of it would vary based on where the lines are nearby. So where it's closer, if I want to sketch this a little bit more, this would have to look something like close and then further out, close and then further out, so as to get more electric field. I guess we should do one more on this side, close and further out. And that way we can see that we have denser lines, so a stronger field, less dense lines, less field. So, which set of equipotential surfaces match this electric field? Our first thing is let's figure out which order we should have, because we'll notice that the top ones are all 0 on this side and 50 on this side, and the bottom ones are all 50 on the left and 0 on the right. So which of those are correct? Well, if we were to release a positive charge in our mind's eye here, it would move that way, because it would move with the field lines since it's positive, which means that since particles move down potential gradients, this must be the direction of lower potential. So we must be in A, B, or C. And then the next question is, well, which of these? Since the field's not constant, the spacing can't be constant. So A is out. And then we say, well, we need to have stronger fields on the right. And stronger field means denser lines. So we need this. So the answer must be B. So that the dense lines are the same as strong fields. All right. Any path that starts and ends at the same point, of course, the voltage is 0, because obviously the potential is defined at a point, so it can't change. So the voltage difference around that loop has to be 0. This comes back to essentially a principle of conservation of energy, that around any closed path, the total work done is 0, so the total energy change will be 0, so the total potential change has to be 0. All right, so the sum of potential differences along any loop or closed path must be 0. This gets a special name called Kirchhoff's law, Kirchhoff's loop law, and we'll use that a lot in circuits. It works in free space as well, but it's historically associated mostly with circuits. And they illustrate here how you might think about it. If we know a couple of paths, for instance, if we have isolines at 20, 30, and 40, well, we know that moving along an isoline, there's no potential difference. But moving from one isoline to the next, you pick up the potential difference. So going from here to here, we've gained 10 volts. Going from here to here is nothing. From here to here, we've gained another 10 volts. So this is 20 volts between here and here. And then going back, of course, would have been minus 20 volts to give us the sum of 0. All right, particle follows the trajectory shown from position I to final position F. Potential difference for that path is which? And here again, we'll use that is basically a state function. So delta V is just V final minus V initial, or minus 50 volts minus 0 volts is minus 50 volts. It doesn't matter that it went up to 50, because it gained 50, but then it lost 100, which is the same as just losing 50. And by the way, of course, 50 volts. All right, a bit of an aside, but potential of a dipole. Remember that dipole is a positive charge and a negative charge of the same magnitude separated by some distance called the dipole distance. We'll call it d. And looking at the two different ways of looking at it, we can draw a contour map. And this is what happens when we add. Remember that the potential is going to be at any distance. Let's see. Let's pick at any point. If we call this R plus and R minus, then the potential is going to be K times Q over R plus, and then plus minus, or plus K times minus Q over R minus. But of course we could do some factoring and make that K Q 1 over R plus minus 1 over R minus, whatever that comes out to be. And if you were to graph this, if you would then take x and y of this point versus what they are, you would get this contour map, showing that the field's strongest in these regions and gets weak somewhat in here, and then falls off as we go out. And then we know that the potential would be high nearby, largely positive, and become more and more negative as we get close to the negative guy. Then over here is what's called an elevation graph, which is sort of just a potential graph in x and y, and we see, you can see the contour circles. And you can see this interesting thing that the line between them is a line here of 0 voltage on that diagonal between them. Why is 0? Because it's plus and minus, but on this line, they're always equidistant. And so these two things cancel out. So that's kind of interesting. Sometimes you'll see this called a pole and a negative pole. And the idea here is, imagine like a tent that's being held up and there's a pole in it. That's more of a math term than a physics term, but you'll see it from time to time. And of course you have that they are dipoles. So that's where that came from. If you wonder like, why do they call them poles? They look like this. You also can see that a positive charge would sort of roll down here and eventually into there, because it would rather be over the negative. All right. At the midpoint of these two equal but opposite charges, which of these need to be true? Well, of course, again, if we think of putting a positive charge somewhere, a positive charge right here, it's repelled by that guy. Let's do it this way. It's repelled by the positive and attracted by the negative. So there is an electric field which is pointing that way, which tells us before we go any further that must be this one. But we also know the potential is 0 because we're equidistant but opposite charges. So again, we'd have, just like we had before, the voltage here is going to be something times the charge times that sort of thing. If the distances are equal, then this comes out to be 0. Same setup, different way of phrasing these things. In fact, we end up with, since these are all basically the same options, we end up with the same answer. All right. At what point or points is the electric potential 0? So now we have to be a little more careful because we don't have dipoles. The potential energy of this one is, we'll call that, is K2Q over R positive. Potential energy of this one is K times 1Q over R negative. And the total potential is just their sum. Again, just algebraic. So I have K times 2Q over the distance to the positives plus K times minus Q, this should be minus Q up here as well, over R minus, which I can factor out as KQ 2 over R plus minus 1 over R minus. If I want them to be 0, then the distance to the positives needs to be twice the distance to the negative. So one of those that's very easy to see is here, because this is 1 unit away and this is 2 units away. But there's also here, because we are 3 units away versus 6 units away. And notice it doesn't matter, it's just distances, so it doesn't matter if they're left or right or point the same direction or whatever. So we end up with C or D.